the Cauchy Schwarz inequality, I think a bit more clear, and it is now the Gram spin optimization, and where we have seen that any set of vectors can be expressed, any set of basis vectors can be expressed as orthonormal basis. Orthonormal means they are perpendicular, not only perpendicular, they have the length unity. They have the length unity. Okay, and interestingly, we have got some nice problem, and where I ended up yesterday. The problem was I have given a vector 8, 5, 11. Given vector 8, 5, 11, and I wanted this to express as a linear combination of basis vectors, and initially the basis vectors were this 1, 1, 2, 3, 2, 1, 3, and 3, 1. And of course, these are not orthonormal basis vectors. These are not orthonormal basis vectors. So, what these are the usual basis vectors which are not orthogonal. And if you express the vector in terms of this basis vectors, you have to so we know that any vector can be expressed as some basis vectors for Vi1. Okay, and what actually happens? Alpha 1, so you can say U. Alpha 1 V1 bar, alpha 2 V2 bar, and alpha 3 V3 bar. Okay, and you have to solve if these vectors, if these basis vectors are not orthogonal. Okay, if these basis vectors are orthogonal, so what we have to do is summation alpha I Ei bar. Okay, and U bar is alpha 1 E1 bar, alpha 2 E2 bar, and alpha 3 E3 bar. So, if these basis vectors are actually given, it is possible to construct orthonormal basis by GS orthogonalization or Gram-Schmidt orthogonalization. What actually is advantage is if you put alpha 1 prime, alpha 2 prime, alpha 3 prime. Here, alpha 1 prime, alpha 2 prime, and alpha 3 prime, they don't have to solve. They can directly obtain by taking the inner product, because E1 dot E2 equal to 0, E1 dot E3 equal to 0. Similarly, E2 dot E1 equal to 0, E2 dot E3 equal to 0, because or E2 inner E3 inner product equal to 0, and because they are the orthonormal basis set. So that's the advantage. So if you want to express any vector in terms of the basis vectors, and the bases are orthonormal, in that case you can quickly find the basis without solving, because solution takes enormous amount of time and a lot of complication. So what I said that yesterday, we solved the problem, we got the alpha 1 to alpha 3, but if you want to express this as orthonormal basis, you can easily write alpha 1 to alpha 3, and without solving, we get alpha I prime. Without solving, we get alpha I prime. Okay? So, with this, I think we have got some fairly good idea on the orthonormal basis vectors. So, now I will start talking about what are the basis vectors and what are the rational ways to construct the basis vectors. And quite often we have heard something called eigenvalues and eigenvectors, right? So the question I will ask, what are good basis vectors? What are good basis vectors? We can say by basis vector, good basis vectors could be 1, 0, 0, 0, 1, 0, and 0, 0, 1. Because the coordinate axis, and these are our standard basis vectors. Okay. So, what I say that, when I say, are they good, that means, are they convenient to use? The question is, are they convenient to use? Are they convenient to use? The next question, are they convenient to use? Okay. So if I say convenient to use, that means we have to avoid the kind of solution. If you have to do the solution, that is not convenient. This is the convenient process. What I say the convenience means, are you getting the the vector or something in terms of basis vector without solving? That means like this, alpha 1, alpha 2, alpha 3. The answer is yes, definitely you can use it. If not, then they are not the good basis vectors. So what I am going to demonstrate here, quite often people say, what are the use of eigenvalues and eigenvectors? So we have seen eigenvalues and eigenvectors. And quite often people ask, what are the use of these eigenvectors? Why we need eigenvectors? And I will show you that for some specific cases, eigenvectors are the good basis vectors compared to 1, 0, 0, 0, 1, 0 and 0, 0, 1. So that's the so we need eigenvectors to get the good basis, and with that basis we can actually solve the system. So we need to now spend some time on eigenvalues and eigenvectors. And before that, rational way, there are so many things that will be happening there. If I have symmetric matrix or if I have non-symmetric matrix, how this basis, how these eigenvectors will be for the symmetric matrix. So, for example, we have 3 by 3 symmetric matrix. We have got 3 eigenvectors. How the eigenvectors are? Are they orthogonal? Are they non-orthogonal? All these things will be coming. If the matrix is non-symmetric, how the eigenvectors will be? There are questions if the eigenvalues are repetitive. For example, if a matrix 3 by 3, I have got all eigenvalues equal 2, 2, 2. So in that case, what are the eigenvectors? They are also repetitive, or they will get distinct eigenvectors. So many questions will be coming in your mind. To address all these questions, we need to understand one theorem which will be useful to analyze the family of the eigenvalues and eigenvectors. Okay, and that theorem is known as adjoint theorem. So we will start learning now. Adjoint theorem. We are starting to learn adjoint theorem. So what I am going to address here, I will write first definition. Consider the operator L on an inner product space, say I, where L star is said to be the adjoint, of L if and only if, I double F, we say inner product LU V equals to inner product U L star V. Okay. So if this satisfies, then I will say my operator is adjoint operator. This L is of course here matrix operator. If L here is matrix operator, I am talking about AX equals to B, which is also known as LU equals to F. U is a vector, F is a vector. U is the unknown vector and F is the known vector. Okay? So, but the thing is that if you ask me what will actually happen for the differential operator, the differential operator, the relationship is similar, not exact. This left hand side is not exactly for the right hand side, and there will be some other terms. Okay, and and those terms will depend on the boundary condition, other features. So let us concentrate first on the matrix operator because we are talking about the vector space, and next is, and of course this U and V, they belong to the vector space, and of course the inner product space I. So inner product definition has to be satisfied. That means inner product definition means there are the properties and all the properties have to be satisfied. If the properties are not satisfied, then we cannot define inner product and we cannot have these properties to be changed. Then next thing is coming as self-adjoint operator. Self-adjoint operator. Please do not get worried about this. I will be deriving this and I will be taking one 2 by 2 matrix to prove what I am saying. Okay. So and of course, any point of the class, you should be able to do your math from +2 mathematics. So +2 mathematics, I am going to bring it here. You will see what actually happens. So self-adjoint operator is if above condition satisfies and if you have very close to L star, then what actually happens? Then the operator is called as self-adjoint. Then the operator is called as self-adjoint, and if the U and V belongs to the real space, then the matrix is called as symmetric matrix. Then the matrix is called as symmetric matrix. So symmetric matrix is nothing but self-adjoint operator. Symmetric matrix is nothing but the self-adjoint operator. Symmetric matrix is nothing but the self-adjoint operator. So now you can see that when you say symmetric matrix, it has to be satisfying the condition inner product L equals to V equals to inner product U L star V, and if L equals to L star, then only it can be self-adjoint, and if U and V belong to the real field, then L is nothing but a symmetric matrix, real symmetric matrix. So next thing is to prove the adjoint theorem. So let's talk about the proof of the adjoint theorem. So I will always write, I will omit this bar and I will simply write this A equals to inner product A. Remember the definition of inner product. Can you give me the definition of inner product? Summation. If it is real space, okay. Otherwise, it is U and V bar I equals to 1 to n dimensional vector space. U and V are both having dimension n dimensional vector space. So I will use. So what actually happens? This A is a matrix, and U is the vector. Resultant is a vector, right? I am multiplying a matrix by a column vector, and you are getting a column vector, right? Okay. And what actually happens? If I say this is W, so I have inner product WV, which is summation WI VI bar I equals to 1 to n. Now W is equals to AU. So how to write? So I can introduce another initial notation, another index called J. With that J, can you express this summation WI VI bar in terms of A and U? Remember that A is the matrix and U is the column vector, and we know the matrix vector multiplication. So I would like to now replace W by AU. How to replace? A matrix typically represented by Aij, right? Matrix A, we have learned already Ij n by n. So Ij is the ijth element. Okay. So what will be the next term? 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 So, what I am asking them, summation I equals to 1 to n, some term will be there. What is that term? Yes, I am sharing so many things. Any hands? Anybody would like to volunteer? Anybody would like to say something? Just yes, madam. Summation J equals to 1 to n Aij Ui. Yeah, this J. Remember that this column and this row has to be same. Otherwise, you cannot multiply. Matrix vector multiplication means this guy's column should be guys know. So it has to be j, and this is the stuff. So what we got finally, summation I equals to 1 to n, summation j equals to 1 to n, aij, uj, vi bar. Okay. So now if you see this index I and j, I can interchange and result will be same, right? They are the dummy units. So if so, you can say interchanging I and j, what you get? Inner product AUB summation I equals to 1 to n, summation j equals to 1 to n, you get AJI, UI, VJ bar. Am I correct? Yes or no? I just interchange. What is that? UI, VJ, because VI bar is now VJ bar. I am interchanging the place of I and j. If I interchange, what actually happens? I will become j, j will become I, j will become I becomes j. That's how we have done consistently, right? So this also you can write as summation I equals to 1 to n, ui, summation j equals to 1 to n, aji, vj bar. This is my left hand side. Let's see the right hand side. Right hand side is u a star v. Now you tell me what is the, how to write summation I equals to 1 to n. If I say this is w, ui wi bar. Okay, so it is ui, then what should I write here? Remember that a star means a bar transpose. A bar transpose. Okay, so what should I write? Summation. We have done just now, same way. Yes. Summation j equals to 1 to n. Just a minute, yeah, please. AJI. Huh? AJI bar will not be there. That's what you got. If you talk partially, you won't be able to learn. AJI bar, then VI. I. Understood? Yeah, why R is coming? And if you don't understand this part, you can do some small work, which is summation I equals to 1 to n, ui, wi bar. Wi is what? Each element is AJI bar, VI, and this entire thing will be done by wi. Okay, you know what mistake we are doing. Now you found the mistake, right? Because all the time you are omitting this wi bar, that was a mistake. Okay, the entire thing has to be bar. So summation I equals to 1 to n, ui, summation j equals to 1 to n, AJI, VI bar. I think it should be VJ. Check it out. Just check it out. This should be VJ. Because yes, AJ I bar VJ. Yes, this should be VJ. Because we are taking the A star, A transpose. Because we are taking the A transpose, that's why it should be AJ VJ bar. Okay. So what actually we got here? We got the left hand side and right hand side are same. And that means the adjoint theorem has to be satisfied. That means the adjoint theorem has to be satisfied. Okay. So let's take up some example. I take some general matrix. Matrix A11, A12, A21, A22. Vector B, V1, V2. U vector, which is U1, U2. Verify. Now I said that, okay, we have done the degree of derivation. Now the school level mathematics is now school level mathematics. AUB. What should I write? You have got the formula here. And all are real, so you don't have to worry about. So what will be my formula from left hand side? Summation I equals to 1 to 2. Summation J equals to 1 to 2. A J I U I. Sorry, A J I U I V J. V J bar, I am saying that all are here. You can neglect the V J. You can neglect the V J bar. So what is my final formula? So now what actually happens? I want the formula V1 and V2, fill in the blanks. I want the formula who can fill in the blanks? So of course there will be V1 and V2 and U1 and U2 and they are multiplied, so I want in terms of V1 and V2. Pardon? A11 U1 plus A12. Next is A21 plus A22 U2. Now right hand side. What's my formula? Summation I equals to 1 to n Ui. Summation j equals to 1 to n Aj Vj bar. So I will neglect the Vj bar because of real field. Okay. So I want you to have in terms of V1 and V2, and you have to come and verify whether you are getting correctly or wrong. Are you getting correctly? Left hand side, first term, right hand side. First term or right hand side. It should be 2. So in that case, one step forward. First you fix I equals to 1, then value j equals to 1 and 2. Okay? So you get for V1 you get A11 for the V1, and similarly if you put 2, it is A12 U2. Okay? So we got A11 U1, A12 U2. Similarly you got A21 U1, A22 U2. Got it? Yes? Yes or no? Got it? So that means this formula again has been verified for the 2 by 2 matrix school level. So school level itself, you are doing something called adjoint theorem without knowing. Now you are seeing that. So this 2 by 2 matrix you might have come across. You might have come across any two vector V and U. Okay, and this is automatically satisfied. Okay. The question is whether the matrix is self-adjoint or not. In that case, A equals to A star. If and only if, then the matrix can be said as self-adjoint or symmetric matrix. Otherwise, not. Now you can ask me for what kind of cases this will not be there. Generally, all the matrix actually follows the rule. I think if the matrix is non-square matrix, then there is a problem to have the adjoint system. The square matrix generally is satisfied. Non-square matrix, there is a question, and that I am not going to address it. Generally speaking, we are always having a square matrix for solving purpose. Because why I am saying square matrix solving purpose? Because when you go for the solving, mostly you are going for the unique solution. Number of unknowns, of course, I am not talking about the number of independent chemical reactions. In that case, you are not going to solve. You are finding a rank of a matrix. For the rank of a matrix, you don't need adjoint theorem. But when you want to solve it, definitely you need to have the adjoint theorem. If you want to find out the eigenvalues, eigenvectors, they are the square matrices. Non-square matrix, we cannot have eigenvalues, eigenvectors. So we consider as for the square matrix, because when you solve A is equals to B, remember that A is the square matrix, and we are currently concentrating for the solution of Ax equals to B. The solution of Ax equals to B, A is the square matrix, and for the square matrix, in general, you see that this is actually like. Any questions, any confusions, any doubts? No questions. Okay. Now slowly I can go to the eigenvalues and eigenvectors. So let's look at the spectrum of eigenvalues and eigenvectors. So for the eigenvalues, I think you all have done eigenvalues, eigenvectors, right? You have done eigenvalues and eigenvectors. So AU equals to lambda U. Okay? A is a matrix. Use a vector such that AU equals to lambda U. Not for any vector. Lambda belongs to numeric field. U belongs to vector space. Lambda belongs to numeric field. U belongs to vector space. Lambda is such a value such that if you multiply this U as the matrix, it is nothing but this vector is magnified. So this matrix is acting as a magnifying glass. Okay? This is a lens. For all the vectors, this matrix will not act as magnifying glass. Magnifying glass or some of the reverse lens you can think about. If lambda is 0.5 or 0.1, this will be minimized. So if I put an object, I put a glass, the object will be bigger size. If I put a object, it could be smaller size. So this is acting as a magnifying glass. The same object will be visible in a bigger scale. Okay, this is a magnifying parameter. Not for all the objects. Okay, some specific object, this matrix will make it bigger or smaller. Okay, and those objects are called as eigenvectors. And those objects are called as eigenvectors. So this is the physical justification. You just think about that. Matrix is nothing but a mirror. Matrix is a mirror or lens. Okay, matrix is a mirror or lens. And some of the objects, not all the objects. I cannot supply any vector. Some vector such that this will be bigger or smaller. And how much is the magnifying parameter? How much is magnifying? That is for eigenvalue. And that particular object is called as eigenvector. That particular object is called as eigenvector. So that's the way you remember. So the eigenvector. And we will see that eigenvectors are one of the good basis vectors. As I said initially, we are now searching for good basis vectors. Because vectors could not be such that we have to solve for alpha 1, alpha 2, alpha 3. If we solve for alpha 1, alpha 2, alpha 3, they are not the good basis vectors. They are not. So we have to get such basis vectors. They are, they can easily available. And our claim is that eigenvectors are those basis vectors. So of course, if somebody asks you whether this coordinate axis are the good basis vectors, you can say they are orthogonal and they are orthonormal. But whether they are good basis vectors or not, that can be a question. Okay? Although it is very easy to see 1 0 0 0 1 0 0 0 1, but they may not be the good basis vectors. So let's look at the properties of this system. So now you see the concept of null space will come in picture. So if you look at AU equals to lambda U, this is your
eigenvector and this is eigenvalue. And if you further write A minus lambda I u equals to 0. So it is nothing but a system called A prime u equals to 0. And we have seen that if Ax equals to 0 and if determinant of A equal to 0, that means A matrix is singular, then X can give non-trivial solution. We have seen that. And they may not be unique, and those solutions belong to null space. So you see whether the determinant of A prime is 0. Of course that is 0. We know that determinant of A minus lambda I equals to 0, right? Which gives a characteristics equation. That means determinant of A prime equals to 0, and that means the eigenvectors belong to null space. Eigenvectors belong to null space. That means eigenvectors belong to null space. Okay. So we have learned lot of things. So now we can see that why we need to know null space. Earlier we were finding eigenvectors. Did you use null space earlier? No? You didn't use null space. For example, I will tell you why null space is required for eigenvector. Matrix A, which is 3 by 3 matrix. Okay? I got the eigenvalue 2 to 1. Okay? My question is, I will get 3 eigenvectors. Are these eigenvectors same? Okay, I have got 3 eigenvalues. And this kind of repeated eigenvalues are quite common. So if I have 3 eigenvalues, out of that 2 are repeated, will you get these 2 repeated eigenvectors and 1 different eigenvector, or you get all different eigenvectors? Pardon? All different. How you can get all different? 2. You can get one eigenvector directly by solving. How will you get another one? That means what? Can you guess how you get another one? Remember that we are solving A double prime, A prime u bar equals to 0. We are solving A prime u bar equals to 0. Okay? We are solving A prime u bar equals to 0. Okay? So what actually happens when you solve A prime equals to 0 for 2, when the eigenvalues are 2, what will be the happening for dimension of null space? I am giving you the clue why you should get to a 2 different eigenvectors. What will be happening the dimension of null space? 3 by 3 matrix, dimension of null space means are you selecting all 3 independently? You know the definition of dimension of null space? Yes. What do you mean by dimension of null space? Yes, one person please, who can give the answer. Can you give me the answer? If the 2 eigenvalues are repeated, why we should get 2 different eigenvectors based on null space? What is dimension of null space? My God, if I have to ask you so many times, I don't know why I am teaching the class. I am asking what is dimension of null space, I am not getting the answer. What is the dimension of null space? I have explained also very nicely, I remember. What is dimension of null space? Nobody is able to remember out of 70 people. I am really surprised. Yes, very hand please. You may be wrong, no problem. Yes.
Number of unknowns minus number of.
Then you are talking so complicated. If I talk like this in the class, it will be okay. I remember that I have been taken out the school level mathematics and explained. You can talk in complicated way. If I talk complicated way, people will say teacher is bad. I cannot say students are bad. To a teacher, students are always good. But the students say teacher is bad because if I teach complicated way. Yes, sir. Oh my God, very complicated. I didn't talk like this. I don't understand number of linear independent. That's why when I talk so simple. I don't expect a simple answer from you. Madam?
number of arbitrary variables.
So these kind of things I didn't teach that way. Pardon? This we are talking very complex. I don't know what is order, what is it, all those things. You are not even sure. You are talking in a confusing manner. You are not even sure. You are talking in a confusing manner. If I have three algebraic equations and I have how many unknowns? More than unknowns. So that means dimension of non-space is what? Oh my God! Again you are saying minus will not be there. Simple one thing. How many unknowns I am fixing independently? That's called dimension of non-space. Boss, I teach this way. Even I am teaching. I am telling you that we are just like in a taken for granted. I am taken for granted. I am taken for granted. If I don't teach bad, you say teacher is bad. Yeah, I teach you. I try my best. You don't care for remembering. Okay. Number of unknowns to be taken to be selected independently. Right. That is called dimension of non-space. We have learned it. But we are saying always minus plus. Math is simple. It's not complicated. So for this case, and if the dimension of non-space will be giving the number of bases of non-space, right? So dimension of non-space will give the number of bases of the non-space solution. If the dimension of non-space is 2, number of bases will be 2, like alpha and beta, remember. Alpha, beta, gamma means each of alpha will have multiplication term and which will be giving bases. So that means what? If I have 2, that means your dimension of non-space must be 2 and you get 2 independent bases, and those are the eigenvectors for 2 and they are different. We have done this kind of problem here for non-space. So go back and try to see that, and I'm really frustrated to see that none of you guys can remember the dimension of non-space. Okay? Anyway, that is your part. My part is to tell whatever knowledge I have. It is your part to accept my knowledge or not. That I cannot force you. I can only expect you know that. Okay. So, basically what actually we found that this U vector is non-trivial and they will belong to the non-space solution, and determinant of A minus lambda I will give lambda to the power n minus lambda to the power n minus 1. We will get trace of A and minus 1 to the power n, determinant of A equals to 0. So you can verify this characteristic equation for 2 by 2 system. You can verify the characteristic equation for 2 by 2 system. How? If my matrix is A, B, C, D, determinant of A is A, B minus B, C. Trace of A is diagonal terms, sum of the diagonal terms. So now, if you want to have A minus lambda I, you can have A minus lambda, B, C, D minus lambda. So determinant of A minus lambda I, which is A minus lambda, B minus lambda, minus CD, BC, sorry. Okay, so it is AD minus lambda, A plus B plus lambda square minus BC. So you got lambda square, and then the next term will be having the trace of it, and the last constant term is nothing but AD minus BC, which is determinant. So the characteristic term equation will have the trace and determinant with the characteristic equation, and this kind of 2 by 2 system is quite important when you do the phase plane analysis. That means when you solve the differential equations, you need to have eigenvalues. And in that case, trace and determinant will play the critical role. So now let's talk about some of the. So now we'll apply adjoint theorem to see how the nature of the eigenvectors and eigenvalues. Okay. So let's. So I'll essentially discuss some of the theorems in this regard. So let's look at some of the theorems here. The first theorem, please note down the eigenvalues. The eigenvalues of the real matrix, the eigenvalues of the real matrix A with its elements as real numbers are equal to those of its adjoints A star. The eigenvalues of a real matrix A in bracket that is with all its elements as real numbers in bracket closed are equal to those of its adjoints A star that's equals to A bar transpose. Why is not clear now? Okay. The eigenvalues of real matrix A, is that okay? Is that okay? With all its elements as real numbers are equal to those of its adjoints A star. Today is the first day, that's not the problem. Maybe here it's better. I don't know. Okay, so I think I have prepared once again. Let's look at the derivation. So we'll see AU equals to lambda U and A transpose V equals to theta V. Okay, I have two matrices. Okay, so adjoint is A transpose, and I'm saying real matrix. That means A equals to A transpose, right? Real matrix. So bar should not come. Real matrix bar should not come. A equals to lambda U and A transpose V equals to theta V. Okay, so U is the eigenvector for the A matrix, V is the eigenvector for the A transpose, lambda is the eigenvalue for the A matrix, theta is the eigenvalue for the A transpose. The questions, what I'm actually trying to say here, we have to prove that lambda must be equals to theta, right? Lambda must be equals to theta. So for the first case, you can write determinant A minus lambda I equals to 0. Am I correct? Second case, you can write determinant A transpose theta I equals to 0 minus theta equals to 0. Right? Yes. And we have seen our determinant formula when I derive determinant. It was already proved. Determinant of equal determinant of A transpose. It was proved already. Right? Determinant of equal determinant A transpose. So determinant A minus lambda I transpose. So when you say determinant of A minus lambda equals to 0, determinant of A minus lambda I transpose equals to A minus lambda. Okay? So I am saying here determinant of A minus lambda I is nothing but determinant of A minus lambda I transpose. With that I can write this same property. Any determinant is equal to the transpose determinant. So what actually happens from here? You can write determinant A transpose minus lambda is a scalar quantity. If you take transpose, same, any number. If you take transpose, same number. I is identity matrix. If you take transpose, you get identity matrix. Okay. Now if you compare determinant of A minus lambda equals to 0, determinant of A transpose eta equals to 0. Okay. Everything is same. So lambda must be equals to eta. Any questions? Any doubts here? Okay. So now I will give 2 by 2 matrix to find the eigenvalues for A and A transpose. So let's take up some of the numerical examples before proceeding to the next theorem. Determine the eigenvalues. So please write down. Determine the eigenvalues of A and A transpose. A and A transpose. A is 2 to 1 3. A is 2 to 1 3. So it is what? So what is the characteristic equation? Characteristic equation is, anybody can tell me what is the characteristic equation? Lambda square minus lambda trace 5 plus 6 minus 4 2 equals to 4. That's the way. So it is very straightforward for 2 by 2 system, because we know lambda square minus lambda into trace plus determinant equal to 0. So what actually happens? What are my lambdas?
1 and 4, distinct eigenvalues. What are A transpose? Verify. 2, 2, 1, 3. Am I correct? And again, if you see the eta, so it is equation is eta square minus eta, 2 plus 3, 5, and 3 into 2, 6 minus 2 equals to 4, and eta should be equals to 1 and 4. So this formula, whatever we have done, it has been derived from in school level. So A and A transpose are the same eigenvalues. Next point I will give 4 minus 20 minus 10 minus 2 10 4 6 minus 30 minus 30. So 4 minus 20 minus 10 minus 2 10 4 and 6 minus 30 minus 30 and minus 30. So find the eigenvalues, and in that case you have to also check the A transpose to verify your results. So next class will be on Friday, and we'll be discussing this problem starting on that and the other theorems. And thanks for your kind attention.